All right, our next talk will be by Martin Schulz. Martin is the chair of the MPI Forum for MPI 4, and his talk is titled, here we go. I guess I get help. It's up on the screen now. Evolving the Message Passing Interface for Future Architectures, MPI 4 and beyond.
All right, thank you very much for the introduction, and thanks for the organizers for inviting me here. When Tony approached me, I thought I'll do kind of a mixture out of a typical State of the MPI Forum talk, as well as looking a little bit forward of where I think we can go and from our point of view should go. Of course, that's open for discussion. And I'm going to go and do this in a backdrop of where our architectures are evolving. That kind of fits very nicely to the talk this morning by Rashiv, who also pointed out the changing architecture and how MPI had to change. And I think we need to continue doing this, and I think we are doing this. So I think we didn't coordinate, but it fit pretty well this way. So, and so looking at these, looking at the architecture, we really have a change in the last couple of years, and I think it's going to continue in where architectures have been evolving to. And we as MPI, we kind of have to adjust to this. I mean, one thing is clearly we're running more and more into power limits, particularly on the European side. This is a huge topic, considering especially the political backdrop right now we have in Europe. So this is a cost issue, there's a political issue, but also running into power density limits. And then there's a push, again, particularly in Europe, towards renewables, which is a great thing, but they're more variable than some of the other power sources that we have. So potentially we have to adjust to this as well, and we have to have more flexibility of dealing with the power that's available at a certain time. We see a big trend towards specialization. That's the typical story of Dinar scaling has ended in the mid-2000s. We're looking at the end of Moore's law any time now. We'll see how long it still lasts. But also here, there's a trend towards specializing, using the transistors in a better way. And that influences how the systems are being designed. Reason is that a general purpose architecture is no longer this one fits all thing that we're used to. Power consumption is quite high for the idea of decoding. So we're paying a heavy price for this general purpose hardware. There's limited parallelism typically in there. And also our problems have become more heterogeneous. Not that we have one workload that fits one particular architecture. We actually need multiple things at certain times as well. And so also here, MPI, I think, needs to adopt and is adopting, I think, fairly nicely to be supporting these heterogeneous platforms more. How can we mix the communication that we need to do with the offloading to the accelerators? We heard some really good presentations today already about this, so I'm really optimistic that the MPI is going in the right direction here. We need to integrate accelerator models with MPI, not necessarily into the same standard, but in a way that we can interface. So I think it's a great thing that we have the OpenMP meetings here as well, because there's a natural connection that's not vendor specific that we can start integrating and seeing how we can cooperate more between the different runtime models, and so we can stay hardware agnostic. But I also think we shouldn't just think about GPUs as with the typical accelerator model right now, but I think there's much more out there. One area we have been thinking more and more in Munich about is quantum computing, and what does this mean for HPC, and we bring this into the fold. It's just one of these exotic accelerating technologies. Then as you think about MPI communicating quantum state, I know some people have been studying looking at this as well, but alone, what can MPI play as a role of bringing the data environments together for quantum systems that typically have a remote machine where you need to ship data to for computation? You need to also ship some of the compute potentially there. And so what role can MPI play with that? How can we extend it, or can we use some of the features that we have for that as well? Would have the really nice feature for HPC developers. They know MPI. If you can actually leverage some of this and bring the familiarity over, that would actually make new technologies easier to adopt and lower the learning curves for that. And so MPI has been doing a lot of this stuff. This is more again back to the point of the State of the MPI Forum kind of talk. And one of the big things I think that has happened here is the partition communication, not necessarily for quantum computing, but in general for hybrid programming and for GPU programming. That was introduced in MPI 4.0. Here the idea is that you can set up your communication beforehand. You can actually have the wait afterwards, and you have a parallel loop in between where you can set up a kernel. These kernels can work on independent pieces of data, and each of these independent pieces of data can afterwards just basically say, my portion is ready, and ship this off. And so we don't have to have a heavyweight operation. This is done out here. You set this up one time, you set up how many pieces you have, and at the end you finish, at the end, all the threads at the end, oops, where's my cursor? All the threads here down here at the end but then each thread independently can do its work and ship things off. I think this has been a really simple addition to the MPI standard, which has a lot of impact and will even have more impact in the future. So we can do pipeline communication with that. We can do, if we have multi-threaded versions, we can prevent serialization from the threads because each thread can work independently, and also leaves much more options for MPI to optimize behind the scenes. And so this is something that came in MPI 4, but the hybrid working group is actively working on pushing this forward. So the question is now, what can we do this for accelerators as well? For example, we don't do a thread here, but we do a GPU kernel now. Instead of the thread, we actually have a GPU kernel running here. We have the same idea that we can start the heavyweight MPI operations on the host. We can then send off the GPU kernel. And then on the GPU kernel, we can basically also trigger communications. We can do certain packing operations, unpacking operations, and then we can trigger these communications. And this can be very low weight, whereas the heavyweight operation is done on the host. So the GPU does what it can do best, and the host can do what it can do best. And with that, we can drive this forward. So this is actively in discussion and in the working group. If you're interested in that, join the hack working group. And I expect this for MPI 5, we will have some features for this available the way things are going right now. Of course, this doesn't come without challenges. One thing is you need to ensure the communication partner is ready when you want to ship something. So there's some API extensions in the works for that. Also, if you notice this here, now we have suddenly something with the MPI underscore in front of on a GPU kernel. So we need suddenly bindings for the different programming models on the GPUs. That opens another can of worms, of course, on how do you even do this? How do you specify the context onto the on the GPU, on the accelerator? So that's something we're looking into as well. And then, of course, the group is also looking on, this is point-to-point for now, what can we do with collectives? And how can we use the same principle also on the collective part? But I think something very powerful that we will see more of going forward. The other thing that we're seeing more and more, of course, is the cost of data movement. Any movement of data is energy. Energy is cost, and we have these power limits, right? And so figuring out how to reduce data movement or at least keep locality going so we don't have to move a long distance is something important. And also here, MPI has introduced some new features in MPI 4.0 from the hardware topologies working group. The idea is if you want to optimize for this, you first need to know where your things even are. You need to understand the topology of your machine, and then you can start organizing your data and your communication based on what you found out of your machine. So querying the existing topology is a huge important thing. Then you can define communicators based on this topology. You now have communicators that reflect some locality, and then you can hopefully with that build topology-aware algorithms. And this was done in 2 steps. You'll find both things in MPI 4.0. The one idea is you can specify where you want to split. So you say, I want all processes on a node, all processes on a socket, be looped together in one communicator. So now I have a really highly local communicator. You specify this, and you specify this when you create a new communicator, and then the MPI will do the right thing behind the scenes. Of course, the problem here now is, as you know, our machines gotten wildly different. Everybody has a different terminology. The cache levels are not exactly the same anymore. What the socket is sometimes also not quite the same anymore. And so having names for this and define the names in the standard, like with so many things in MPI, would have brought us into something very implementation specific, and we didn't want to do that. And so this is an implementation defined way to specify this. You need to know what your levels are. But if you don't know what your levels are, there's a second mechanism in the MPI 4 standard as well. It's called the unguided mode. And here's basically where you kind of explore your environment. You start with the MPI COM world, and then you shrink yourself down. You say, what's the next level down that's of interest? And you get communicators for that. And what's the next level down? And what's the next level down? And you can see by this picture that I stole from one of Guillaume's presentations. You start with the blue one, which is everything. You can find out if there's green would be the rack part, and you would find the NUMA nodes, you would find the CPUs, and so on. And with that, until the end, you end up with an MPI, with a single MPI process in your communicator, and then you have found the whole hierarchy, and you know that you can work based on this hierarchy. And the assumption is the smaller it is, the more tightly located it is together. And you can do this recursively, again, to identify the topology to work on. So I think, again, a very powerful mechanism was introduced in MPI 4. We'll have to see how well MPI developer, application developers can utilize this, but I think this is going to be a powerful mechanism to do more locality-aware algorithms. And then the last thing is also you have a more diverse workload. I mean, not just doing modeling and simulation anymore. Like this is the big thing that we basically grew up with in MPI, but there's more AI workloads, there's more data analytics workload, and also quantum workloads. This is, again, a different flavor of what they need from HPC are coming up as well. And so also here, we're going to have to be a bit more diverse. And then overall, you see what I see personally as the trend here. We have to be more variable, right? We need to adjust to power limits. We need to adjust to different accelerators in our system. We need to adjust to the topology. We need to adjust to the right workload that we have, potentially multiple types of workload, even with one application. And so we need to have a much more adaptive system going forward, and the software stack that we're building has to also reflect that. And so this will also, I think, will lead at the end to breaking some of the dogmas we have been having in HPC for a long time. And also the MPI kind of has grown up with. And so that's also why I think we need to have some changes here. So one of the big dogma is that we typically have is one node, one job. Oops, there's an E missing, sorry about that. So one node, one job. We're seeing really big benefits of looking into co-scheduling, of putting multiple jobs together onto a node, particularly if you have multiple accelerators on that. Some jobs may use the accelerator, some may use the host. So they're very complementary, and they could utilize a node together in a much more efficient way. This can work within workflows. This can work across applications. This can even work within kernels of an application, depending on what granularity you want to do this. But this idea of just running a homogeneous workload on these highly heterogeneous adaptive architectures, I think, will lose us some efficiencies. The second thing, what we've gotten used to is the jobs have a very static resource usage. You allocate 500 nodes, you get 500 nodes, and you stay with 500 nodes until your job dies, independent of what you do with them. Right now, also this, I think, is not efficient anymore. So I think dynamic job allocation, expandability, like we heard from Dominic's talk earlier as well, I think can be really beneficial here, adapting to external conditions, seeing where we have the right resources, where we have the right, where there is contention, so we can perhaps back off a little bit, where there is free space, so we can go into that, will help a lot. And then the other thing on the power side, we currently still have a lot of machines that are done on the worst case and fixed power distribution. This has gotten much different. It's more and more systems that are kind of going away from this already, but going to a much more dynamic power stack, the kind of dynamic power allocation that allows us to steer this across the nodes, to figure out where do we need the power most, where can we reduce power requirements, and with that balance the system and stay within a power limit or in an energy limit that we have for the systems. Particularly if you have in a constrained situation, or if in a situation where the constraints fluctuate, potentially because of renewable energies, wind and solar die off, the total grid can't provide the power anymore, you would have to reduce the power that you take into the center. These kind of things will be very helpful going forward into this. And so this requires a couple of things that we need to do to make this work. That also directly affect MPI. The one thing is we need to first understand what our system is doing. If we want to be adaptive, we need to know what the system state is so we can know what to adapt to. We need this across this whole stack. I think developments like EuroMPI are extremely helpful for this. This is the news, is a idea for a new generation of MPI profiling, which doesn't just do a single layer of profiling, but allows you to stack multiple profiling parts. And the reason why this is helpful is because now you can have user tools and some optimization parts that come from the application side, coupled transparently with system and runtime monitors, which are below the scenes, which basically always run, but without taking away the slot to run a user tool. And we can now take this information, feed this into a data analytics engine, and can understand of what are the codes doing, what is the behavior of the codes from the MPI level, from the communication level, and grab this information transparently without influencing what the application can do in point of tooling. And then the second step of that is take this information and put it into kind of a database for in situ data analytics, particular operational data analytics, ODA. A lot of centers have started doing this with various different pieces. We have our own solution at the Compute Center in Munich called the DCDB, the Data Center Database, where you have a whole bunch of plugins that grab sensors from things like the MPI layers, but also from environmental sensors, from on-node sensors, performance counters, and kind of store this whole thing in a very fine-grained interval, store this whole thing in a hierarchical fashion in a database so you can do analytics after the fact, but you can also do tuning through different plugins for data analytics engines on the fly as well, on the nodes as well. So you can also use it for automatic tuning, but you can also use this for analysis afterwards, and again, understand what your system is up to and how you can optimize your system forward. So this is a critical component that we need. Without that, we wouldn't be able to kind of do the next step. But then once we have the information, we can now adjust the system, right? So we can now understand what is going wrong, where we have optimization potential, and then just drive this based on that. We can do it in the system side as the first step, and kind of a closed loop system optimization, where we can find out which resources are overused, which resources are underutilized, and kind of give hints to application, give hints to the systems on how to do this. And we're doing this particularly in the area of active power shifting, so we can actually take components that may be running too hot, we can give them more power and take power away from systems that don't need it, or we can balance the power more in this direction. This is part of our EuroHPC work called Regale, where we have this layer in the multiple layers from the system, nodes, application side. We combine this with the monitoring, and we have managers on the other side that then take this and optimize the system based on that. This is also very closely related to the power stack work we have been doing together with several partners. And this is kind of the first European implementation of the idea of a dynamic power stack. And then there's the last part that I wanted to talk to, and that's where MPI comes back into the picture. We also need to do the software stack more dynamically, the programming abilities more dynamically. And this, of course, should be in the evolution of standard models, including OpenMP and MPI. Again, I think it's great that the two worlds are together here and kind of interact here. There's a lot of things that can be done in domain-specific libraries and frameworks, but we need the adaptivity first in the underlying systems, because if we don't have it there, then we can't bring this up to the application. And also, I think this can be very nicely combined with fault tolerance. I'm not sure if we need actually special fault tolerance solution. If we have the ability to generally adapt the system and react to resources going away, we just have to know to react to immediately going resource, and we basically have fault tolerance as well. So this may be a very nice unifying theme that we can build up here and have for future systems. And so we need this adaptivity across the whole runtime stack to have more efficiently utilized resources, to also counteract variability. I think we can't avoid variability anymore. And so if we are more adaptive, we can actually adjust to that, and with that kind of help ignore it, even if we can't eliminate it anymore. We're going to have much more complex workflows. Also, those require adaptivity, and also these new workflows that we already talked about, right? And so this needs this adaptive resource management in all pieces of the software stack, including MPI. And there's a second European project that focuses exactly on that. So it's the EuroHPC project Deep Sea, where the goal is to build such a comprehensive software stack. This is kind of the EuroHPC idea. For those of you who haven't heard that, this is basically a counterpart to some of the efforts in the US and the ECP project to build up a European HPC infrastructure from the hardware, system software, all the way to the applications. And this is one of these projects in that area that built that software stack up, and that kind of course, take a lot of in from the community, but with a particular focus on adaptivity and adding this adaptive feature to the software stack and making it available afterwards for the European exascale machines, which are currently being procured and built. So the focus is again on heterogeneous machines, which we all expect exascale machines to be heterogeneous. The software goes from the driver all the way to the programming abstraction. And the central theme, as I said, is this idea of malleability that we're focusing on. And the work you heard from Dominic before fits into this project. We're not going to go into technical details because you heard that already, but this is kind of the theme where the whole idea comes from. And so we need to figure out how to make this possible. First of all, we need applications that actually are willing to try this out and willing to do this, that either over decompose or virtualize some of these resources so they have these right properties for that. And then we need to be able for them to request and to drop resources so they can actually work with that so it makes sense for the application. So this is, of course, a kind of a chicken and egg problem. The question is which applications are useful for this, which applications can actually do that. And so one of the big applications we're using, and Dominic was already alluding to that, is a parallel time solver, which has exactly these properties. It's a third EuroHPC project called TimeX, which looks at parallel time methods. And then this is a close connection to the other projects and how to make this work together with a software stack. And this is very nice in the sense that this is an application that can request resource, can add resources on the fly, or can remove resources on the fly. But it's not an application that just always grabs more and more and more, right? Because some applications can always use more resources. But no, there's actually nice trade-off points. At some point, the return on investment is not there anymore. So it's the application basically has a performance model built in. And when does it make still sense to ask for resources? And when does it actually make sense to give back resources because the return on investment is not there anymore? And so this is coupled with a kind of a decision model of what to request, recoupling this with what the system can offer. And then you have this combined model where we can find the sweet spot, both for the application and for the system. And that's kind of the big demonstrator we're working for to show how this can work as one of the applications. And then there are several other applications we're kind of looking into as well. But this is kind of the key driver for this work. And I think it's going to be a very nice demonstration at the end. And then also the other thing is for an application to actually make the decisions, of course, we need to capture dynamic state. And so I want to just mention one project that we're also up to as part of the deep sea work. We need to capture the kind of the topology that we have in a dynamic way. A lot of systems give you a static view of that. But if you now want to be in a dynamic environment, you also need to capture this dynamically. You need to figure out which attributes this has. You need to be able to expand this as well. So we're developing a library called SysH, which kind of works on a similar idea than HWlog, but in a dynamic sense, where you can also get more information in than just what HWlog does, but basically from the whole system, as well as runtime information as well. We can capture this, we can capture the topology of the system. And the way we're doing this, we have kind of a dual representation. You have a component tree that gives you the hierarchical view of the system. This is in the standard static view. And then there's a data graph on the side of that uses then connections between these components and describes properties and dependencies between these, and those can change over time. And so we can kind of figure out what is the static base system and kind of how does it evolve over time and give that information back to the application to make decisions of where to drive this and kind of where to optimize the potential system and how to adapt this. And so MPI, of course, it has to play a big role in this now. We can only make this available for the applications if we support this in MPI. And MPI is, as we all know, not the best player in this. With a very static MPI-COM world. We have moldability theoretically, technically in the standard, but nobody actually does it this way. Nobody checks how many processes you actually got after you start up an MPI chip and see if this matches what you requested, even though you technically should do this. We have dynamic resources as well, but again, nobody has been using this and has been rarely implemented, particularly in centers. So I think there's some ideas in there already, but we need to work a little bit to make this work. And so the question is, how can we change MPI to support this malleability? We have to change some of the abstractions, particularly around COM world. But on the other hand, it's really important to keep the look and feel of MPI, because otherwise you may just well invent another model, right? We want to have existing applications be portable to this, to kind of work with this environment in the right way. And I think the MPI sessions that were introduced in MPI 4 are really a nice way out. And Dominic already gave an overview of that, so I just want to run through this really quickly for those of you not familiar with the session idea. But basically, it replaces what we're doing with the initialization, it replaces MPI init, and it replaces MPI COM world. And this is how we get out of this box of these very static, initially allocated resources, because we don't have them in the first point anymore, and then we can live without them going forward. The way sessions work is you allocate a session which gives you a handle, you get a set of processes, these process sets that Dominic was talking already about. You can get a group from that. And so far, everything is local. There's nothing from the MPI point of view global here or collective here. So we can do this all local, hopefully all very efficient. There's a runtime system behind it, which of course has to do some communication, some pulling threads together and setting up connections. This is totally clear. But from the MPI side, this is first of all purely local. And the first time we actually have something that spans processes is when we create that communicator at the end. And so if we do the first part right and we just slice and dice in the right way, we get a group that's exactly what we want. That doesn't have to be the whole world, and that we can create the communicator from. And when we do this a second time through, we may get different process sets. We can slice and dice different, and we have a different world that we can create again. And so we can have this independence of things in there, and we have more, we can implement the right adaptivity. So this eliminates COM-world. This allows us to deliver runtime information to the MPI library by querying this set of processes. We can also use it the other way to communicate to the runtime system by extension that allow us to create these processes, and then it enables this isolation between sessions as well. And so we have basically two different worlds running at the same time, to say it simply. And with that, we're not bound to this one static world anymore that the current model has. And on top of that, we can then build and provide a path to have this ability to be more dynamic by having this query option. So, for example, runtime can add new process sets to a session when something grows and shrinks, when new resources become available. This may have to be combined with versioning potentially. You can also start new sessions which have new process sets, for example, by providing new info objects and saying, I kind of want to have all sessions that work on this communication medium and then work on this communication medium if you have a node that's connected to two networks, for example. Or you can specify, I want certain nodes that have certain requirements, and you only get a subset of what would be available otherwise. So you can also here be much more dynamic. And then also we have the idea of potentially manipulating these process sets. You saw this again in Dominic's talk earlier, where you can take a process set, you can slice and dice it, and republish that. And this also gives you an ability to interact with the runtime system. So these are all just ideas, but this is kind of where I think we can go, and this is also what's happening currently in the working group. What's still missing, this also came out of discussion beforehand, which I didn't know when I put the slides together, is that handshake API, right? So we now know how to deal with the process sets, how to set this up. But when do we really request resources? How do we request resources, and how does the resource manager react to that? That's kind of the next step. How can we find out what is new? How can we then negotiate for that? And how can we transition then from there cleanly? So this is kind of some of the activities that are going on. And if you're interested in that, please join the MPI forum, join the sessions working group. I think there's a very active, interesting discussion going on, and I always welcome more participation in that. And of course, if you haven't already planned for this, stay for the forum, of course, where this will also be a central part of the discussion in the second half of the week. So to conclude, basically, so I think we're seeing that the HPC architecture is getting more and more diverse in point of parallelism, accelerators, and workloads. And so we need MPI to change, and I think MPI is changing and reacting to this in the right way. And we're still focusing on communication, but some of the interaction with the node local models, I think are being more prominent and being more prominent developed. We're supporting the heterogeneous and hierarchical systems better, and also the malleability is coming up. And I think in MPI 5, you're going to see even much more going things in this direction. And the MPI sessions, because they take away some of the problems that we have, this kind of static resource view is taken away with the sessions without affecting all the other calls, the other flavor of MPI, I think can be really a key vehicle to form this, to drive this transition. It has the isolation part. We can do potentially even revoke resources that are just bound to a session without having a global impact. Again, I think this could also be a very good, clean solution for fault tolerance. We can also have this interaction with the runtime systems. What we still need is these interfaces to negotiate with the resource manager. That's kind of the next step we're looking at. Before I finish, I want to acknowledge this is, of course, work done by a lot of people in the different projects, in the different teams like DCDB and also the partners. Of course, the forum, one thing, particularly the sessions working group led by Dan and Howard, and the Power Stack initiatives that we're working on with a whole bunch of people as well. And of course, our team in Munich, as well as our funding agencies. And with that, I'm happy to take questions. Thank you.
Mark, a quick question. So a lot of this, remember we had this big push, Ian Foster, Jeffrey Fox, for this grid computing thing that no one talks about anymore except Rajiv's here. Grid FTP, good. Yes. Okay. But we use that. That's a ubiquitous tool. But this grid thing with grid descript, there was RSL. There were these things we actually used to hook up MPIs like over the network between. We didn't deal with fault tolerance so much. We did that later separately, but we were making these grid computing things. This sounds like grid computing again, because you're trying to shrink and grow, grab resources. And there's a whole bunch, there was huge investment in grid computing. So I just asked the general question, how does this stuff with the MPI and flexibility, morphing and elasticity relate, if it does, to grid computing or anything learned in grid computing?
That's a good. It's a good question, and I think what you're addressing is actually kind of a danger we need to pay attention to a little bit. There is a lot of similarity, but I still see MPI to be kind of within the HPC system at the end, right? Not connecting something across continents, right? You could use it for that, but I think we want to be careful not to go too far, to go in this direction. But we certainly can borrow some of the ideas on how to describe a resource and things like this. We shouldn't invent the wheel in that one, right? But I think that the focus of the discussion should be within an HPC system. I don't see MPI really spawning multiple HPC systems for arbitrary grid computing, right? Yes, you could drive it this way, but I see the danger that we're going to thin ourselves out a little bit there.
So, Martin, these things that you talked about, the sessions and others, to me, it seems still like sort of a band-aid. In a sense, at heart, MPI still is kind of static, the application model, and that's right. So now the working groups are proposing this session and the PMX. Do you think we should radically think differently? What's your opinion on that? Obviously, you have if you come up with a radical model, then nobody will adopt it. But will we run into this band-aid, and then again, at some point, it doesn't work? What's your opinion?
I mean, that's a tricky question in the MPI forum, but I mean, I think the model of MPI, once you get going with it, having a kind of fixed set of resources for a certain time, I think is a very clean model. And that's kind of why it was introduced, why models like PVM failed, right? So I don't think we should give this up completely. And also we don't want something that changes all the time, right? I mean, there's like every second you get a node and go away. There's supposed to be coarse grain changes in the thing. And in these coarse grain times, you still have your quote unquote old MPI model with all the benefits of knowing what you're talking to, knowing how you structure your communication, right? So I think otherwise you would have to go through algorithms that constantly change, that constantly readjust. And I don't think that's the right model either, right? And so, yes, it is kind of a band-aid. What would we do it differently when we start from scratch? We probably wouldn't have the idea of this world anymore. We would probably start with something like sessions right away, right? And that would actually take a lot of the stuff away, because a lot of the problems we're seeing in sessions is actually not so much the sessions themselves, but having the sessions and the world both at the same time in the standard, and always having to refer to what happens if in which model, right? And so that's the band-aid I think we have. That I think will rip off at some point, but this is probably definitely beyond my time as a chair. So for the folks on the Zoom, the question was, what would we look at more the broader communication mechanism, like for IoT and for like new types of applications? I think we could look into that, but again, it's the same thing about what Tony said before. I think a lot of stuff applies, but at some point, I think we're diversifying too much that we're losing the core idea of it, right? At some point, it's not the right thing anymore. Yes, we can always push it a little bit more and make any communication MPI, but I think at some point it doesn't make sense anymore because we're losing our core values, right? And so where that line is, I don't know. I think exploring is always good. Whether we then actually pull this into the standard is a second question. And again, that's for the discussion in the whole forum then to decide whether it's worth taking this on and putting, as he said, another band-aid on to make this work, right?
Any other questions from the room or from the call?
This is not meant to cause trouble, as you know.
Sure not, of course.
One of the points, and I'll bring up because Ron will be here. Ron Bright will be here tomorrow. But one of the things he pointed out is one of his views, and I want to give him full credit for this. So if you think this is trouble, in between, you could think of that could be.
So as far as workflows goes, I think actually MPI can play a nice role with that. The sessions may again be something that will drive that, because a workflow component could be a session that has its MPI interior without having to know about the other components, as if they would be independent programs running, right? So I think this could work, and I don't think this would take us too far off field. I think we actually have most of the features already. There's a matter of trying it out and experimenting with it, and then seeing what works and doesn't. See if you even need extensions for that, because I think you could do most of that stuff or stuff already to some degree. I think the fault tolerance has to change a little bit, because if one component dies, you don't want the whole system to die. I mean, you could even go as far as saying the whole resource manager should work on MPI. Why not? As a communication, it creates a session when it starts a job, or creates a session for a component to start a job in, right? I mean, this could be done, but then of course we need to have a completely different view of what it means to be fault tolerant, and not at the fine grained level of individual process dying, but kind of reasoning about blocks of processes and kind of how to arrange them. I think it's possible. I think actually we don't need much more. I think it's more of someone going out, trying it out, and coming back with experiences on it.
All right, let's thank Martin one more time for the talk.
Thanks.